Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this video we are going to solve problem 9.1, chapter number 9, gas turbine cycles, from the book Applied Thermodynamics by Eastop and McConkey. The statement of the problem is a gas turbine has an overall pressure ratio of 5 and a maximum cycle temperature of 550 degrees centigrade. The turbine drives the compressor and an electric generator, both. This is the schematic: compressor and turbine. This turbine operates this compressor as well as here generator is coupled with this turbine. The mechanical efficiency of the drive being 97%. The ambient temperature is 20 degrees centigrade and air enters the compressor at a rate of 15 kg per second. The isentropic efficiencies of the compressor and turbine are 80 and 83%. Neglecting changes in kinetic energy, the mass flow rate of fuel and all pressure losses. Calculate the power output, the cycle efficiency and the work ratio. While for the solution of this problem we have to assume Cp and gamma as 1.005 kJ per kilogram per Kelvin and 1.4 for air, and for combustion and expansion processes we will assume Cp is equal to 1.15 kJ per kilogram per Kelvin and gamma is equal to 1.333. So first we will write given data. Pressure ratio is 5, P2 by P1, and it is equal to P3 by P4. This is the overall pressure ratio for both compressor and turbine, and it is 5. Maximum cycle temperature is T3, so T3 is equal to 550 degrees centigrade, and if we convert it to Kelvin it will become 823 Kelvin. Mechanical efficiency is 97%. This is basically the drive efficiency. The ambient temperature, which is T1, is 20 degrees centigrade, and if we convert it to Kelvin it will become 293 Kelvin. Isentropic efficiencies for the turbine and compressor are given. Also mass flow rate is given. So mass flow rate is 15 kg per second. Isentropic efficiency of the compressor is 80% or 0.8, and the isentropic efficiency of the turbine is 83% or 0.83. We are required to find 3 terms in this problem. First, we will find the power output. Second, we are required to find the cycle efficiency. And third, we will find the work ratio. So coming to the solution of this problem, with the help of these expressions we will find the missing temperatures and once we find those missing temperatures, then we will be able to find the compressor work input, turbine work output, drive efficiency, network, power output, work ratio, and cycle efficiency. So coming to the solution of this problem, first we will find temperature T2S, this is unknown. Remaining P2, P1 and T1, also gamma, are known. So using this expression directly, I am writing it for T2S. First we are interested to find the value of T2S, so for that it will become T2S is equal to T1 into P2 by P1 power gamma minus 1 by gamma. Now putting the values, T2S is equal to T1 is how much? It is 293 Kelvin, and pressure ratio is 5. Gamma value for air is 1.4 minus 1 by 1.4. So simplifying this, the value of T2S comes out 464.05 Kelvin. Now from the definition of the isentropic efficiency of the compressor, we know that the isentropic efficiency of the compressor is equal to T2S minus T1 over T2 minus T1. So in this case we have T2 which is unknown. So from using this expression we will find the value of T2. So for that we can write it like this: T2S minus T1 is equal to T2 minus T1. This isentropic efficiency will go there, so it will become denominator divided by isentropic efficiency of the compressor. So rearranging it again for T2, T2 will be equal to T1 plus T2S minus T1 over compressor isentropic efficiency. So putting the values, T1 is 293 plus T2S is 464.05, T1 is 293 divided by isentropic efficiency of the compressor is 80%, 0.8. So simplifying this, the value of T2 comes out 506.8 Kelvin. Further, at the expansion side, we are again required to find some missing temperatures. One of them is T4S in this expression. As P2 by P1 is equal to P3 by P4, so pressure ratio is known in this case, T3 is known, and the value of gamma is given, which is 1.333. So only T4S is unknown. So using that expression we will find the value of T4S, and it is equal to T4 is, I am directly writing the expression, so it will become T3 by T4 is equal to P3 by P4 power gamma minus 1 by gamma. So now I am interested to find the value of T4S, so rearranging the expression for T4 is, it will go there from cross multiplication and it will become T3 by P3 by P4 power gamma minus 1 by gamma. In this case gamma value is 1.33, so putting the values, T3 is how much? It is 823 Kelvin divided by pressure ratio is 5 power, gamma is 1.333 minus 1 by 1.333. So solving it or simplifying it, the value of T4 is comes out 550 Kelvin. Now from the definition of isentropic efficiency of the turbine, we have an expression here. Isentropic efficiency of the turbine is given by T3 minus T4 by T3 minus T4S. In this case only T4 is unknown, so using this expression we will find the missing temperature, which is T4. So first writing the expression for the turbine isentropic efficiency, and it is T3 minus T4 by T3 minus T4S by T3 minus T4S. So in this case we have T4 which is unknown, so from cross multiplication turbine efficiency will be multiplied with T3 minus T4S and it will become equal to T3 minus T4. So again rearranging this expression, T4 is equal to T3 minus turbine efficiency into T3 minus T4S. So putting the values, T3 is how much? It is 823 minus turbine efficiency is 0.83 and the value of T3 is 823 minus T4 is calculated, which is 550 Kelvin. So simplifying this, the value of T4 is equal to 596.41 Kelvin. So all the missing temperatures, which were T2S, T2, T4S and T4, were found. Now it's very easy to find the work of compression and the work of expansion. Now using these temperatures we find the value of compressor work input and turbine work output using the expressions Cp T2 minus T1 and Cp into T3 minus T4. So I am directly putting the values in those expressions. First, the work output from the turbine, which is represented by Wt, and it is equal to Cp into T3 minus T4. So Cp is 1.15 kilojoule per kilogram per Kelvin for expansion side, T3 is 823 and T4 is 596.41. So simplifying this, we get 260.57 kilojoule per kilogram. Also, for finding the compressor work, it is Cp into T2 minus T1. So this is basically the Cp of the gas side and it is for air. So Cp for air is 1.005 kilojoule per kilogram per Kelvin. The value of T2 is 506.81 minus T1 is 293 Kelvin. So simplifying this, we get 214.87 kilojoule per kilogram. Now to find the net work, we will take the difference of these two terms, which is turbine work and compressor work. So turbine work is 260.57 minus compressor work is 214.87. So simplifying this, we get 45.7 kilojoule per kilogram. Now we are interested to also incorporate the mechanical efficiency or the drive efficiency, and it is equal to generator work divided by net work. So from this, if we find the generator work, we will multiply the mechanical efficiency with the net work. So generator work is equal to mechanical efficiency into net work. So we now here incorporate the drive efficiency or the mechanical efficiency, and it is 97%, and the net work is 45.7. So when we multiply it, we get 44.33 kilojoule per kilogram. So in all the calculations now further, we will use this generator work, because in this the mechanical efficiency or the drive efficiency was incorporated. So now we find very easily the value of power output, that is equal to generator work into mass flow rate, and mass flow rate is 15 kilogram per second. So generator work is 44.33 kilojoule per kilogram into 15 kilogram per second. So the value of power output comes out 664.95 kilowatt. So this is the first part which was required to calculate. Second, we have to find the cycle efficiency. For that, we will need the heat supplied. So heat supplied in this case is equal to Cp into T3 minus T2. So when we put the values, Cp will be 1.15, T3 is 823, and T2 is how much it is? 506.81. So simplifying this, the heat supplied is equal to 363.62 kilojoule per kilogram. Now we can find the cycle efficiency. Cycle efficiency is equal to, in this case, when we assume the losses as well, that is the mechanical efficiency term. So in this case we will use the generator work, which is 6644.33 divided by heat supplied is 363.62. So the cycle efficiency comes out 12.19%. Also, third, we have to find the value of work ratio. So work ratio is equal to, again in this case we will use the 44.33 value, and it will be divided by the gross work, and the gross work is 260.57 kilojoule per kilogram. So when we simplify this, we get 0.17 or 0.169, so it is almost equal to 0.17. So this is the overall solution of problem 9.1, in which we were required to find the value of power output, and second we have to find the cycle efficiency, and third the work ratio. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.